and I will direct a few questions and then we'll open it up completely. I'll be introducing each speaker as we proceed. I'm going to start with Dr. Ed Crawley. Ed is a professor in the Department of Aeronautics and Astronautics at MIT. He has been the chairman of that department. He holds a number of chairs at MIT. He's Ford Professor of Engineering, as well as Professor of Aero and Astro and of Engineering Systems. He was a member of the 1993 Presidential Advisory Panel on the Space Station redesign. He recently co-chaired the committee of the National Research Council's review of the NASA Exploration Technology Development Program, and most recently, he served as a member of the Review of Human Spaceflight Plans Committee, the Augustine Committee, about which one heard briefly from Norm Augustine earlier this afternoon. So Ed, I wonder if you'd start us off with some discussion of the flexible path and how it relates to our plans going forward.
Thank you, John. I'm going to step up and walk over here with the mic so that I can look at the charts along with you. If we can go actually back one, I entitled this talk, which is based pretty directly on the findings of the Augustine Panel, although there's a few additional editorial comments, a new exploration strategy. Because I think at the highest level, that's what the discussion that the President presented today is about. That this is not only a new place to go or a new way to get there, this is really a new strategy for exploring space. In the Augustine Panel, we actually began in a remarkably coherent system engineering way about thinking about what the goals were for human exploration, that human exploration is a credible partner of science, that it develops technology both for space, for NASA, for other users of space, and for use on the Earth, that it produces economic development and industrial capability, and that, of course, exploration prepares for further exploration. That these are the tangible benefits, and then, of course, particularly in the policy environment, there are less tangible benefits. U.S. leadership of international ventures, the soft power that comes from leading international endeavors, engagement of the public, and particularly inspiration of the youth. Now, at this point, you're saying, why is he reading off these platitudes? Because this is more or less the list that we all acknowledge, and in fact, most of this is expressed in the Space Act of '58. Well, the reason we read that I'm spending time on this list of platitudes is that to have a sustainable space program, you actually should do these things. How's that for a revolutionary idea, right? And in particular, I will quote the words from the letter of the 3 Apollo commanders that was distributed earlier this week, American heroes for whom I have the highest admiration. They said, Apollo inspired a generation of Americans. And it did. And I'm here along with the President as a result of that inspiration. But exploration is not about venerating the past. Exploration is about inspiring the leaders of the future. And the most important one of these that we found the most disconnect in the Augustine Panel this summer with is the inspiration of youth. We found very few young people who were inspired about going back to the moon 50 years after we had been there. It was a tremendous accomplishment, and they've read about it in the history books. We actually applied these platitudes towards helping select a strategy, and we called them goals. And I'll ask you the rhetorical question. Did the previous program inspire America's youth? Did the previous program engage the public? Did the previous program demonstrate effective leadership of international endeavors? Did the previous program stimulate economic development? Did the previous program develop new technologies for use by NASA, other users of space, and the general public? I ask these rhetorically, but these are important considerations that go directly to its sustainability, that we actually tried to craft a strategy that would do these things. Next slide, please. And in, I think, a remarkable moment one evening this summer, this very diverse group of panelists from industry, from government, from academia, from science, from technology, all very quickly and unanimously endorsed this statement, that Mars really is the ultimate destination for human exploration of the inner solar system. That staying on Mars and extending human civilization within the solar system should be our goal. That this is difficult, it will require a lengthy commitment. We actually heard the president say that he hopes to see some of this happen in his lifetime. But it's a time to begin along this pathway. And that these goals, the goals expressed in the important policy documents that have been promulgated by both Republican and Democratic administrations that are central to the Space Act, should guide our exploration. Next chart, please. Now, this one chart sort of summarizes as best I can the thinking of the Augustine panel this summer. That we started off and said, well, we got all these questions. Should we do something with the ISS or retire it? Should we go to the moon or something like the flexible path to Mars? And very quickly, we actually arrived at the conclusion that we should not disregard the ISS, but embrace the ISS. That the ISS really is a laboratory that we can use. And I should say that this was not a panel of ISS huggers. This is a panel, many of whom were on record at one point or another as having said the ISS was perhaps not the greatest investment of NASA's 20 years of effort to build it. So this is sort of an only Nixon could go to China moment. You know, that these previous critics of the ISS said, now we can envision a strategy that engages the ISS and uses it. And I'll come back to that for a moment. Okay, so then that leaves the moon, the flexible path, Mars. Well, the next conclusion is you can't go to Mars now. That we don't have the technology and we don't have the national treasury to do it and do it safely. So we then moved Mars off into the long-term goal that we should move towards Mars, but we should not plan to go and land on the surface of Mars in the immediate future. And that left us with, after the ISS, these two intermediate pathways, going to the moon or going along the deep space part of the flexible path, exploring, going to Lagrange points, the asteroids and so forth, as the president discussed earlier. Now, I'll ask you, if you were the president in 2035 and the administrator of NASA came to you and said, Mr. President, we have spent the last 10 years going to the moon. We have developed the capability to land on planetary bodies and to rove around and explore. But no American or no international partner has ever been more than 3.5 days away from the Earth. We're ready to go to Mars on a 900-day mission. That's not a credible explanation. On the other hand, if you'd been on the flexible path and you'd spent a decade or so exploring deep space, going to libration points and so forth, and asteroids and orbiting Mars, but had not since Buzz and Neil and the others were there, landed on a planetary surface, would you say that we're ready to land on Mars? Also probably not. So in all likelihood, before we land on Mars, we'll have done some combination of both the deep space part of the flexible path and done some test flights to the moon. And the only real question is one of order or sequence. But these give us two types of capabilities. They teach us and they allow us to develop the operational competence to work on a planetary body and to work in deep space away from in the full radiation dose of deep space. So that leads us to this lower corner diagram. And when you do this, you realize the ISS actually can now play some new roles. The ISS can play the role not only of human physiological studies and so forth, but of things like experimentation and fuel transfer. It could actually even be an operational base for early missions. So this is the diagram that I'll leave you with for a second. Next chart. So what is the flexible path, as we discussed it in the Augustine Report? It's a new strategy. It's to travel many places in the inner solar system, but initially not walk on the surface. There are over 100,000 bodies in the solar system inside of the radius of Jupiter. And by my count, you can only land on 4 or 5 or 6 of them. The Moon, Mars, 2 of the Galilean moons of Jupiter, and maybe a few of the largest asteroids. All the rest of them you would visit by going near them and bumping into them or making samples of them or operating around them, much like you operate in the vicinity of the ISS. They either don't have the gravity to sustain a landing, you would just bounce off of them, or they're inhospitable enough, like Venus, that you would never venture down to the surface with humans. So the idea that we're going to explore the solar system by landing on things is actually more a rarity than the general rule. Most of the places we might want to go, you actually want to encounter, not land. And when you encounter, it creates a new opportunity for a synthesis of robotic and human exploration. You get near the body, you send out probes. You robotically capture samples. You bring them back for analysis. You operate telerobots on the surface. I hesitate to say this, but you basically enter a standard orbit, scan the surface, and send down a Class A probe. Some of you remember that reference. So this is a strategy that is, as the name implies, flexible. It's enabled by capability, and it's guided by discovery. Next chart. Now, if you sort of plot out where you might go in the inner solar system, it's interesting that the world sort of falls into about 3 bands. And the most important parameter here, as all the rocket scientists in the room know, is the energy increment represented in delta V from low Earth orbit. And you notice there's a whole set of things, the Earth-Moon Lagrange points, lunar orbit, or Sun Lagrange points, near-Earth objects, and a Mars flyby, that are a relatively modest delta V increment from Earth orbit. And then there's the lunar surface, and then there's getting to the surface of Mars. And remember, the rocket equation is not linear, as I would say in one of my classes at MIT. It's highly nonlinear, so it's significantly harder to get 10 kilometers a second of delta V out of a system than 5. So it's actually, the difficulty in moving to the more distant locations is underrepresented by this plot. So there's this set of things that if you could move around with about 5 or 6 kilometers a second of delta V, you could travel lots of places. And let's look at what they are. Next chart. This sort of represents a schematic. First, you would probably go to lunar orbit. Or, interestingly, we didn't put it in the report, but another alternative is geosynchronous orbit. It would have interesting service implications and, frankly, security implications if Americans could routinely travel to geosynchronous orbit. I would consider the orbital flight, this is Apollo 8, go to the moon and orbit it. That's test flight. That basically says to the world, we could return to the moon anytime we chose. I'm not convinced that we need to win the race to the moon to be the first nation there the second time. We've been there. Well, some of us have been there, Buzz. Then we go to the Earth, Moon, the places, the Lagrange points, and I'll talk about those in a second. Then the near-Earth objects. And then in 2025 or 2028, the NASA administrator and the president can decide what the right, depending on what we've learned and what capabilities we have developed. We could go to the lunar surface. We could go to Mars flybys. There's some very nice missions that go to Mars and sort of get a deceleration in the vicinity of Mars, spend some time there, get another acceleration off Mars, come back, so that you could actually operate in a flyby in the vicinity of Mars for a reasonable amount of time. And they all eventually end up with some sort of landing on the surface of the moon. Next chart, please. So here are a sampling of the places you could go on the flexible path. This chart is in the report, but I want to spend a little bit of time on it. But not too much time. Thank you, Mr. Chairman. I'm almost done. So there are the destinations on the left-hand side. There are types of things that you could use to engage the public that you can see listed here. There are opportunities to do science in most of these places, and my other colleagues will speak about that. But the column on this chart that actually causes it to make sense is the one called human research. The big unknown about going to Mars, or going anywhere other than the surface of the moon, frankly, is the human adaptation to prolonged weightlessness, radiation, and psychological stress. And if you were to design a research program, you would design it in such a way that you did a couple of weeks of this, a couple of months of this, a half a year of this, a year of this, a couple of years of this, and steadily, like in a Gemini-like mode, build up the competence to do it. And if you read down the human research column, you see that somewhat by coincidence, but luck favors the informed, the choice of these destinations causes a sequence of human exposure and human duration that allows us to develop the confidence for the length of missions necessary to go to Mars. Last chart. Or next chart, I'm sorry. This is just it sort of laid out as a timeline, which I'll skip over. Next chart. This is actually a more interesting view. Now, I have to warn you that these are figures from the Augustine Report, which assumed a higher budgetary level than is in the President's current plan. But it gives you some sense. At the top is what would have happened if we had run out Constellation, invested in technology, and extended the ISS. And you can see that it causes a lunar landing to occur in the late 2020s with an additional, as Norm said, $60 billion of investment over and above the President's FY09 budget. If we do the flexible path, we get out of low Earth orbit by the early to mid-2020s, shortly after the ISS might wrap up. And there's a sequence, a steady cadence of trips to new places beyond the Earth-Moon system on an annual basis. Next chart, please. And the reason why this sequence makes sense is really very simple, especially if you've ever been a project manager. There are essentially 4 big pieces that you have to develop in order to land on a planetary surface: a heavy lift vehicle, a capsule, a lander, and a surface infrastructure. If the first destination is the surface of anything, you have to build all 4 of those systems before you can go. If you use this deep space route to the flexible path, you can build the booster and the capsule and start going. So that, roughly speaking, in the 20s, you'd operate the deep space systems and build the planetary surface systems. So that in the 30s, you could operate the planetary surface systems. Next chart. So just to summarize, these are the things that are the benefits of the flexible path. It's a faster start. You get out of low Earth orbit sooner. You go to destinations humans have never been, inspiring America's youth. There's a regular cadence of exploration of new things. You are developing the deep space capability you need to go to Mars. There's an authentic synthesis of humans and robots. Opportunities for interesting science. You get this beneficial development profile. You have an opportunity to engage international partners in a new way, and it represents generational change. I think this is, in some sense, the most profound thing. This is a way that young people today would think about exploring, and it will engage them and make progress towards our ultimate goal.
Thank you very much, Ed. I'm now going to turn to Dr. G. Scott Hubbard. He was the program manager of the Lunar Prospector mission and was the first Mars program director at NASA headquarters, successfully restructuring NASA's approach to Mars exploration after a number of failures. He is a past director of NASA's Ames Research Center and the NASA Astrobiology Institute, served as a member of the Columbia Accident Investigation Board. He's currently a professor at Stanford University, where he works on the study of both human and robotic exploration of space, as well as continued research in astrobiology. Dr. Hubbard.
Use this microphone, and so I can see the charts. Let me build on the excellent introduction by Ed Crawley. Go to the next chart. I want to talk primarily about robotic exploration and the beginnings of the true convergence of robotic and human exploration for both science, national interest, inspiration, return on investment, and the other platitudes that are nevertheless real objectives of the space program. And I want to say something that I haven't been allowed to say for a while, but under this new program I can say space exploration is human exploration. Sometimes, thank you. There were times when the twain never met, but now we're allowed to say what we're really doing. Humans are sometimes physically present, as Buzz was, but many times we send our robotic emissaries. Now, robots are terrific at the 3Ds, the dull, the dirty, the dangerous work, and they generally do what you tell them to do. Humans, however, we've got 2 million years of evolution in our current form, and our eye-brain-body combination gives us unmatched adaptability in an unstructured environment. And that's the key, because if you're going to a world you've never been to before, you need to be able to prepare to react to the unexpected. So, consider all the science goals the National Academy has been looking at. Many of them can be very effectively and efficiently done without human intervention on the surface. However, there are a series of science goals where humans would be particularly, even exceptionally valuable, particularly picking out samples and making judgments about what science to do, how to react to being around another world or on the surface of another world. I think this budget advances both of those goals. So next chart. I'm going to talk just a minute about what I think is the scientific heart of exploration. Astrobiology was a term invented for these purposes about 14 years ago now, almost 15. It only has 3 questions. Where did we come from? Are we alone? Where are we going? Easy questions, very tough to get the answers. But this synthesis, this multidisciplinary convergence of sciences seeks to find the answers to these questions by looking at things like, is an environment habitable by a living system, and what are the fingerprints of life out there in the solar system? Next chart. So let me turn to Mars. Since Mars has been designated by all these studies groups as the ultimate goal, why Mars? Well, it's the most Earth-like of the planets, most likely to have had or even possibly have today life on it, and it's reachable every 26 months, unlike the outer planets. And the theme that we adopted in the restructuring over 10 years ago was follow the water. And why water? Because water is necessary for any life form as we know it, liquid water. And it is a common thread among science goals of living systems, the evolution of climate, the solid planet geology, and human exploration. So following the water provides us with the resources for putting humans on the surfaces of Mars in particular. Next chart. So today's Mars exploration program, as Dr. Holdren said, was redefined about 10 years ago. I got the chance to take a nearly clean sheet of paper and put a new mission queue together, grounded in science, but also based on the availability of technology and programmatic constraints. And that mission queue ended up with Mars Global Surveyor, Mars Odyssey, the twin rovers, the Mars Reconnaissance Orbiter, the Phoenix Scout, and coming next year, the Mars Science Laboratory. And these missions sought and seek to understand Mars as a system. Next chart. So following the water, how have we done on that? Water is a key to life, climate, geology, and future human exploration. And here's how you explore a world. First, you look from orbit. As we said, in the flexible path, there will be orbital missions. Mars Odyssey, launched in 2001, found evidence for enormous amounts of water trapped in ice in the top 3 feet of the red planet, up to 50% or even more at the poles. But this is information from orbit. Is it really true? You need to get the ground measurement to convince yourself that really you're seeing what you think you're observing. So next slide. The Phoenix mission, a few years later, went to the North Pole of Mars, found the ice, confirmed that by onboard chemical measurements. So now we know that if the moon is moist, Mars is soaking wet with hundreds and hundreds and hundreds of millions of tons of water ice at the surface, and probably, we hope, liquid water further beneath the surface where it's warmer. Next slide. So let's take one other picture. Mars Global Surveyor, launched in 1996, showed on the right a Connecticut-sized part of Mars that had minerals, as seen from orbit, that are always associated, at least on Earth, with liquid water. But do we really know what we're looking at? The way we explore a world is first to make observations from orbit and then go to the surface and confirm that with ground truth. Next slide. So the Mars rovers, these incredible machines, they're in their 5th year of operations. The warranty was only good for 90 days, and they're still working. And if you click the slide once more, you will see that what you were observing from orbit was a Connecticut-sized field of these little blueberry-type spheroids of a mineral that only exists from long contact with water. Plus, we also saw the ripples characteristic of moving water. So this is how we understand what's at Mars, how we're beginning to understand the evolution of Mars, and why Mars is such an appealing target for future exploration. Next slide. So what's coming up next? This is the sequence of the family tree of rovers. We began all the far right with the little toaster oven-sized Sojourner from Pathfinder. And then quite deliberately, in the restructuring of the program, went to a sort of small golf cart-sized rover, maybe 300 pounds or so, which has sent back an incredible array of postcards from Mars, which just happens to be the title of a book by the gentleman in the front row, Jim Bell here. And coming next is a metric ton on the surface of Mars, the Mars Science Laboratory that this budget fully funds, that will take the most extraordinary analytical laboratory ever built for the surface of another world to Mars. It's an astrobiology instrument, and this rover will be capable of going tens of kilometers. It has radioisotope power, and it will land very precisely all technologies that are necessary to build toward the ultimate human exploration of Mars. Next slide. So with all of these really capable rovers, with this investment in autonomous systems and systems that we drive from the Earth, why do we need humans there? What can they do the robots can't do? And rather than reading this to you, I'll just tell you the story. This is a story Steve Squires, who is here, not in this room, but at this event, tells. They were out doing a field test. Jim, were you there for this famous experiment? Okay, so out of field test, there was a technical problem. So Steve says to the assembled population of Mars experts, let's do a little examination here. I've got a stopwatch, standing out in the field or out in the desert. I want to start the stopwatch. I want you to find something that's interesting, go pick it up, tell me what it is. So, go. So here's Ron Greeley, famous expert of Mars. He looks around, he goes over, picks up a rock, breaks it over with his rock hammer, looks at it with his hand lens and says, Jarosite. Click. Total elapsed time, 45 seconds. To do that same piece of analysis, current robotic technology takes hours, days. So again, having a human being there with all the expense it requires would bring us back an enormous amount of scientific data. Next slide. But to get there, the challenges, as Ed Crawley said, are significant. There's affordability in both budgetary and human terms. There are the biomedical problems, and we have to have the technologies in place. Next slide. So some of those, from my past role at NASA Ames Research Center, we did a great deal of work on intelligent systems and autonomous systems. I can say that the information technology challenges are things like management of large data sets, autonomy and mobility, and then the human-machine interaction and the telepresence interface that was being spoken of a little while ago, the ability to orbit a body and operate with very quick light travel time a rover on another world. Next slide. So this is the picture. This is a different way of looking at the flexible path. Shows things we learn from the space station, the heavy lift possibilities, the expeditions to the near-Earth objects, the missions ultimately to Mars, and then down at the bottom, the robotic missions that may precede the human exploration, so-called precursor missions. And I want to propose the possibility of one, next slide, a Mars sample return campaign. This would be the convergence of science, extraordinary science, the astrobiology community, and indeed, I believe the whole science community dealing with planetary exploration would agree that bringing back samples of Mars will tell us a huge amount about the evolution of that planet and about the potential, the biological potential for that planet. It is going to be an international mission, I would say, because of the complexities of sending a lander to the surface, sending the sample up to orbit, rendezvousing with the sample, returning to Earth, and it will also be a precursor to human exploration because it will give us measures of the soil, the toxicity. It will be an end-to-end demonstration of traveling all the way to the surface of another world like Mars and coming back. So what's the future for exploration? It's not, as it has been for maybe 50 years, robots versus humans. It is, last slide, humans and robots working together. And I think this is what the new program can bring to us, and this is what the new program will invest in. Thank you very much.
Thank you, Scott. Our final panelist is Dr. John Grunsfeld, PhD in physics from the University of Chicago, started his career as an astronaut when he reported for training in 1992, a veteran of 5 space flights, including 3 missions to service the Hubble Space Telescope. He is popularly known as the Hubble repairman. He served as NASA's chief scientist from 2003 to 2004, is now the deputy director of the Space Telescope Science Institute in Baltimore, Maryland. John.
Thank you very much. It really is a pleasure to be here back at the Kennedy Space Center, where I've left the planet 5 times, and I have many of my astronaut colleagues here in the audience as well. Exploring the cosmos. Scott has done a great job of motivating the case for Mars, but it's a very big universe. Next slide. And I'd like to make the case that I think we all know science is exploration. Next slide, please. Science attempts to answer very fundamental questions, at large. How did the universe begin? What's been its evolution? How did the first stars form? How did galaxies form? How did the chemical elements that we're made of form, and where did they form? How did planets form and solar systems that allow us to be here to have this discussion about how we leave the planet? Next slide, please. I truly believe we're born as explorers. We're born as scientists. Even before we can talk, we're trying to understand how the world works. We're also trying to find food and what's good to eat and what's not, but that's a whole other story. But we're constantly reaching as children. We're constantly absorbing new information and trying to synthesize models to try and figure out how things work. Next slide. So in this 2011 budget that's been proposed is an extremely strong statement about the importance of science in our country and in the world, and specifically the building blocks, the innovation to allow us to make new investments to look towards the future. Next slide. Science at NASA is incredibly vibrant and vital. From Voyager, the first spacecraft that's leaving our solar system, to the Solar Dynamics Observatory that we've just launched that's going to allow unprecedented studies of the details of our own sun. We live around a star, and we still don't understand how it works. To the Hubble Space Telescope, a favorite of mine, as you've heard, the Chandra Observatory, the Spitzer Telescope, all exploring the depths of the universe. We have the Cassini spacecraft doing space exploration, and as you heard, it's our surrogate explorer out at Saturn. We have the wonderful Mars rovers, and we have the Kepler spacecraft that's discovering new planets orbiting nearby stars, when only 20 years ago we didn't know about any of them. And this is just a very small fraction of all the science that NASA is currently doing. Next slide. Of course, the most important planet in our solar system is planet Earth. And we know that there's climate change. We know that we have an impact on our environment. And one of the things that I think is tops in this budget is that there's a significant commitment to Earth science and trying to understand the Earth as a system. Until we can do that, and it's a very difficult problem, we're not going to make progress in being able to make good policy decisions. And one of the keys to that is to make good measurements. And so there's an enhancement in the budget to try and develop new missions and new sensors to understand the behavior of the climate of planet Earth. Next slide. So, at large, where should we go? And if you can key the mouse. As you've heard from Jack Crowley's talk and also from Scott, from Ed Crowley's talk and from Scott, there's lots of places we can go. Low Earth orbit, lunar surface, deep space, near-Earth objects, Mars, going beyond Mars. All of these are potentially acceptable. So what metrics can we use? If you could click again. We should go to compelling places that offer unique opportunities to extend our human knowledge and at the same time to use as building blocks to go the next stage in exploration. Next slide. So Mars, the challenge, how do we get there? And it's amazing what you can do with Photoshop these days. That was a picture of the moon. So what this policy and this, the plans that the President outlined today offers, and as Ed Crowley said from the Augustine Committee, is stepping stones to get there. Extend yourself further and further. And we start with robotic precursors. And so something I think is extremely interesting would be the opportunity to rendezvous with a near-Earth object. Some of these near-Earth objects are future potential threats to Earth, but they're also scientifically extremely interesting because many of these are building blocks of our solar system, and we don't understand them very well. One part of this is I think it's very important that as we build these robotic precursors, we put them together as building blocks that can play together in other destinations, and that we build a real modular infrastructure. Next slide. Of course, as Sylvia Earle said when asked about ocean exploration, a famous ocean explorer, why do you go? Why not just send robots? And, as the human in her, she says, because I want to go. I want to see with my own eyes. And there is that human perspective, that human intuition in place that allows for, markedly faster progress. And here's a picture at the bottom from the Mars Exploration Rover Opportunity, and at the top is a photograph taken by Apollo 17 astronauts. And I just want to point out, if you could click the mouse, there's a person in the upper picture. And I really do believe that that makes a big difference. Just go ahead and click the mouse. That's Gene Cernan there walking on the moon. Next slide. I do think it would be compelling to go to a near-Earth object and explore. Here's asteroid Itokawa, and it's pretty big. As you heard, you don't really land on it. Charlie Bolden talked about that. You don't land on it. You rendezvous next to it and kind of float near it. You can see the International Space Station and a prototypical capsule to scale. It would be quite a phenomenal mission, and it would extend our experience into deep space, into a radiation environment we haven't seen before. And also, by going to a near-Earth object, an asteroid, and perhaps even modifying its trajectory slightly, we would demonstrate a hallmark in human history, the first time that we show that we can make better decisions than the dinosaurs made 65 million years ago. Next slide. As Scott said, it's all about a human-robotic partnership. Robots have never discovered anything. People discover things. People discover things using robots. And in Scott's cartoon, he showed a picture of a robot helping a human out of a crater, and this is actually a future astronaut rescuing the Mars rover Spirit from Troy at home plate out of its tough spot with a little bit of a winch. Next slide. What about risk? Going to space is risky. Sitting on top of millions of pounds of explosive fuel is not exactly the sanest thing in the world to do. There's always going to be risk. And the further out we go, the higher that risk is going to be. People thrive on risk, but in the end, we have to take risks that are important. And for my personally, in my risk-making, the Hubble mission was something that was worth risking my life for. And as this Houston Chronicle editorial says, the Hubble repair mission showcases the value of manned space flight. And we take these risks when the outcome, when the reward is really great. And this is another metric we can use to decide on where to go. Next slide. Of course, I'm going to pick my favorite experiment, and the experiment is the Hubble Space Telescope. By having this wonderful combination of humans that are adaptive, that bring their insight on the scene, we've been able to upgrade the Hubble Space Telescope and really rejuvenate it and expand its capabilities many-fold, 5 times in space. Here, installing the advanced camera for surveys in 2002. This remarkable ability of having the space shuttle and people is what enabled the Hubble to make many of the discoveries that it's made to date and will continue to do for many years. We have a real opportunity with this new plan to develop new technologies alongside the requirements for science so that together they're much more powerful than they would be if we weren't to combine the human-robotic partnership for human exploration with the scientific motivation. Next slide. So just some examples from very recent history. In January, the Hubble Space Telescope observed what's probably the first collision that we've observed in the asteroid belt. Things collide over long time scales all the time, of course. That's what broke them all up. But here's a photograph with the Hubble Space Telescope of the result of one of those cosmic collisions in the asteroid belt. It may be a collision like this that caused something to come in and hit the Earth 65 million years ago. In the middle slide, you see actually the first visible light image of a planet around a nearby star, in this case around Fomalhaut. And so we actually imaged the planets. That's in the little inset. And on the right is a picture that we never imagined we could make when we launched Hubble. And that's a photograph of galaxies as they were 600 million years after the Big Bang. The light from those galaxies has traveled for over 13 billion years to reach Earth. We're seeing some of the first galaxies that formed in the universe. Next slide. This budget also fully funds the James Webb Space Telescope, the next very large telescope, and that's going to extend our ability to answer these fundamental questions. What was the first light? When did the first stars turn on in the universe? How did those stars form into galaxies? The births of stars and planets occurs tightly shrouded in the dust and gas of these star-forming regions, the beautiful things like the Eagle Nebula. And the James Webb Space Telescope will be able to peer into those regions where stars are formed. And we'll also be able to study planets and perhaps start looking for the origins and the environments where life might form on another planet. Next slide. The next step, though, beyond the James Webb Space Telescope, if we really want to be the generation that can answer that question, are we alone, we're going to need yet another telescope. And this is something that could be enabled by the development of a heavy lift booster with a much larger fairing that could take a telescope even bigger than the James Webb Space Telescope, one that would be required to image this very faint light of a pale blue dot, and then using physics determine that there's oxygen and water and methane and maybe other organic compounds in the atmosphere of that planet that would conclusively, in principle, find out we're not alone. And of course, here's a fake Time magazine cover saying, we are not alone. We're right on the fringe of being able to do that with the next generation telescope. And of course, I think that's June 2028. Next slide. Is it that long? Seriously, 2028? Well, we can discuss that. As we service the Hubble, with this modular architecture, with the ability to go to further destinations, we have the opportunity to build modular systems such that we could service these new big telescopes and other spacecraft the way that we've serviced so successfully the Hubble Space Telescope, vastly expanding their scientific potential. Next slide. Of course, in the end, much of it's about inspiration. We have lots of complex challenges in our world, and we often say, well, technology will solve those problems. Well, where are the scientists and engineers that are going to solve those problems? Where do they come from? NASA is a very powerful engine for inspiring students, and I think there's a strong commitment from this administration to support that, and science is one of those things that kids get very excited about. Next slide. Of course, it's a lot about the NASA team, and this NASA team is truly excellent. The folks that I've worked with are truly the best and the best of the best, and I'm convinced with this new opportunity, we'll be able to kickstart exploration and do wonderful things. But it all comes back to Florida. Next slide. This is a picture I took of my crew. I may have taken it, of Florida not quite a year ago, and the question is, how do we proceed? So hit the mouse if you would. I think the key is cost-effective low Earth orbit transportation, as we've heard. The journey always starts and ends through low Earth orbit, and we need it to be cost-effective so we can afford to do these other things. The heavy lift is critical. The heavy lift is critical in terms of exploration, but also in terms of science, to be able to bring up the large payloads, to be able to assemble them in space. I think a modular exploration architecture is critical so that we can do things like space servicing, and we can visit different destinations in a way that's cost-effective. In terms of inspiration, we do need frequent and compelling missions. And we also need those creative partnerships, NASA with our international partners. Science is the international language of peace. It is going to be a planet-wide effort to do tackle some of these hard problems, but also partners in government with our contractors, our commercial and academic institutions. But in the end, it's not all about Florida. It's also about Congress. Next slide. I actually wrote this down one day in the House Science Subcommittee room. There's two things written on the wall, and I think this one's very forward-looking. And I've modified it slightly, but it's from Tennyson. For I dipped into the future, far as human eyes could see, saw the vision of new worlds and all the wonder that would be. I'm often asked to summarize things in 25 words or less, and I think I'm only going to use 4. So if you'd click the mouse. I think this new plan supports science. And cue up the words, if you'd click the mouse one more time. Innovation, innovate, explore, discover, and inspire. And I'll leave it with that. Thank you.
Thank you very much, John. I think we've just heard and seen 3 extraordinary presentations from 3 extraordinary people. There are some other extraordinary people throughout the audience. In fact, I suspect everybody in this room is an extraordinary person. I want to direct a few questions to some of the folks that I've noticed in the audience. And, of course, it's not surprising that I noticed right away Buzz Aldrin sitting in the front row. Buzz, you were the second person to set foot on the moon quite a while ago. But you're also a remarkable example of looking forward and not just backwards. I know that from some extraordinarily interesting conversations with you. What's your take on what we've been talking about today?
I have a great appreciation for all of the professorial remarks. I tried being a professor for a while, and I just got tired of wanting to go over the obvious. I have always wanted to go over the unobvious. I think that started when I was maybe a second lieutenant in the Korean War. I didn't move up a flight. I wanted to get into operations. Squadron operations. So when one guy didn't come back from a mission, he's a second lieutenant, I took his place in assistant squadron ops. Then I got into assistant group ops. And I met John Glenn, who was an ops officer in one squadron, and I told him how many F-86s he could put on the Yalu River. This gives you a little bit of power when, as a youngster, you begin to tell. But his squadron commander one time really got pissed off at me because he thought I had shortchanged him. The Statute of Limitations is, in reflecting back, clearly I made a decision not to get into perfecting the present, and that's a test pilot. I had a desire to look at the big picture, how can we do things better? And when I found out between alert with nuclear weapons in Germany that the magazine in 1959 said to be an astronaut you had to be a test pilot, I thought I'd really missed the boat. But education made the difference at MIT, and I'm happy that 2 people up here have been through course 16. You were MIT also? Wow, we really outnumber Stanford. I'll have to tell my wife about that. So I feel that I am an enabler to the places we want to go. How do you do it has been the challenge for me. If we want to go to certain places, we have the capability, but how do you do it? Recently, I had the occasion to re-examine what made Apollo work. Having studied rendezvous at MIT, of course, I and many other people would say, well, what made Apollo work was lunar orbit rendezvous. I see John shaking his head. In re-examining that, I believe what really made it work was specializing the spacecraft. We developed a spacecraft specially to go from Earth to the moon and back again. Then we developed a spacecraft to land. Now you have to make that work for human beings, and you need to make rendezvous work. I have had a great admiration for John Holdren for a long time, and that's what prompted me to try and improve on what he did. And wouldn't it be nice if you could have something that just kept going back and forth from Earth to the moon? Well, it's not that easy. And then it was painful to my ego to find out that even if you did do that, it really wasn't very useful for taking people from the surface of one place and taking them to the other. So Tom Paine said to me, why don't you look at Mars? I was very daunted by that because I knew how complicated Earth to Mars would be. But if you take the seat of your pants and look at orbital motion that way, that's what led to opening up the way of using gravity assist, which had been used to go further and further away, to maybe don't go further and further away, but make a cycling orbit out of it. I got exposed to something called NIH, not the National Institute of Health, but not invented here. And if you have a good idea and the government didn't think of it, it probably isn't a good idea to the government because they didn't think of it. And I think that's true for industry also. I would say that we need to look at implementing further missions by how we can implement them. And every mission that I've seen going to Mars goes direct to Mars. Doesn't stop anywhere else, but the design reference mission that was so useful in Apollo, one mission, and we kept doing it over and over again, the design reference mission to go to Mars goes to Mars. But I was aware of a study that had been made a long time ago of what can you get out of different possible missions. We can fly by Mars, we can land on Mars, or we can almost land on Mars and see what we can do. And that brings me to this moon rock. It's not from the moon, but it's a replica of a Mars moon, Phobos. If you are able to put humans on Phobos, so what? What do you get out of it? Well, it's easier to get there. From a delta V standpoint, it's easier to get to Phobos than it is to the surface of our moon. Just takes a little bit longer. Now, what can you do when you get there? I asked Steve Squires, because I had some ideas that if you had people there, that might be quite useful, since they can transmit to the robot and control it directly, whereas the closest a robot is on Mars to Earth is 4 minutes. And it can be as much as 20 minutes if it's on the opposite side. And as a result, anyway, to get to the point, 5 years of Spirit and Opportunity on Mars, according to Steve Squires, could have been done in 1 week if we had humans on the moon of Mars, Phobos, or on the surface, but I think in orbit there means you can relay to other orbits, and as you move around, you're always going to be able to see what you're looking at down there by relay stations.
We really actually don't even have time for any more questions because at 5:30 over in the Astrobiology Theater, Charlie Bolden's going to start the wrap up.
Ooh, I thought that was 5:40.
We have to start moving now to get over there. Do you want to do
Okay.
two more questions?
Let's do one or two more questions.
Did you, are you? Okay.
There are just lots of steps outward, and one of them is going out and coming back a year later. That doesn't get to another object, but it allows you a free return trajectory. And you can take that free return trajectory, and if the engine quits at any point, you're still coming back, except it's not as big in orbit. But if you design it to fly by a comet, just think what you can do on a free return trajectory that goes close by a comet. Not too close, but Lacrosse mission says, let's do something with the upper stage that's going along with you. Let's crash it into the comet as you fly by and take pictures of it.
You can see that Buzz Aldrin is still an endless source of ideas for which we're grateful. I want to ask Lori Leshin, who is the NASA Deputy Associate Administrator, to reflect on what we heard from Scott and John about the interaction between humans and robots and what we learned from exploring with each, by telling us a little bit about NASA's plans going forward in that dimension.
Thanks very much. Yeah, I'm the Deputy Associate Administrator for Exploration, the Exploration Systems Mission Director, and I'm happy to be up here to present some balance, as I went to Caltech, not MIT. So we need some diversity in schools here. So obviously, as we heard really eloquently today from the president and from the panel, the goal of this human spaceflight endeavor is to really create a sustained capability to send humans into the solar system to stay. And whether your interest is in science or in economic development or in long-term human habitation on other worlds, there are many interesting destinations, as we've heard about today. There are asteroids, and obviously Mars, and even the moon has a lot of interesting secrets to unlock in the future with humans and robots. So one of the exciting things in this program is a set of robotic precursor missions that are going to give us the knowledge we need ultimately to create this sustained human capability in the solar system. So at ESMD in the last couple of months, we've been putting plans together for these robotic precursors, and I thought I would just take the opportunity to tell you a little bit more about them, about what we're thinking. So that the basic objectives here would be to find safe and interesting sites to visit, to have these robotic precursors be scouts, to understand the resources that would be there for humans so that they could one day live off the land on these objects, and to also understand the hazards that exist in these places that we want to go with humans. So we're looking at several different approaches to getting this kind of information, whether they be standalone missions of sort of medium class up to $800 million or so. Also some small, quick getaway kind of missions that we're calling them exploration scouts that could be quick turnaround missions. Also tons of opportunity for international and commercial participation in this robotic precursor program, where we could have payloads on international missions. We can partner with the commercial community with their capabilities to get this information for us. And the kinds of things we're talking about are following up on the exciting discoveries of LRO and LCROSS that hint at water on the moon, and can we actually extract that or other resources and utilize them? Can we operate robots on the moon remotely to get at that human-robotic partnership that Ed Crawley talked about so eloquently, either from here on Earth or even from the ISS? We will be looking at missions that can do that. On Mars, can we get at the toxicity of that dust? I would argue we could actually do that with a sample return mission that doesn't even land. You could fly through that atmosphere and sweep up some dust and do your first Mars round trip really soon as a great pathfinder to future human round trips. And in 2018, the Mars opportunity is the most energetically favorable in about 30 years. It'll be a great opportunity for us to test new landing technologies that will allow us to break the 1-ton barrier that the Mars Science Lab is going to just approach up. We have got to land more mass on the surface of Mars if we're going to send humans. So in 2018, we're hoping it'll be part of an international armada of missions to Mars to prove out some of those human precursor capabilities. And asteroids, there's so much more that we need to learn about how, what they all look like, what are the diversity of possible targets there, how would we operate around them. So bottom line is, I think the details of where we go and when are going to be driven by the discoveries we make in the next few years with this robotic precursor program and with the technology development programs that are in this budget. We're really excited to get started and get going.
Thank you, Laurie. We have about 2 minutes left. I see Bill Nye, the science guy, sitting in the front row, and I want him, as a world-renowned expert on inspiring kids, to tell us whether we can inspire kids with this vision going forward.
Absolutely, we can inspire kids. If you want to know why we're going to go to Mars, ask your kid, ask your grandkid, and he or she will tell you. Now, Buzz, is it true that if I'm on Phobos with enough mobility in my spacesuit, I can put a tennis ball or baseball-sized rock into orbit? Right? You can throw it into orbit. Yeah, we encourage you to turn the rock when you reach back. Don't go like this. You want to turn your fingers. So you're going to have proper mobility in your glove. So yes, if ask a kid why we're going to go to Mars, and he or she will tell you. The whole thing is there's 2 questions, or 3, Brother Scott. Where did we come from? Are we alone? If you want to answer those 2 questions, if you want to get closer to those answers, Mars is the next destination. That's it. So let's go have a look. And in order to do that, we have to have programs that are not only sustainable economically, but politically, so that each time we achieve a goal, the public, people, taxpayers, and voters will sustain it. Let's change the world. Thank you very much.
Thank you, Bill, and I want to thank all of the panelists. We now need to call it to a close and go on to the next stage, but this has been a terrific session. I apologize to those who would have, I know, added to the richness of this discussion with their own comments, but we just didn't have enough time. Thank you again.